All right, this video is going to show us how we can use Hess's law of heat summation in order to figure out what the enthalpy of our chemical reaction will be. Okay, scientists need to figure out what the enthalpy will be before they do different chemical reactions because they don't want to be surprised. They don't want to have something overheat and melt the canister or cause some sort of severe reaction where something could freeze or melt. And so they, instead of just mixing things together and YOLOing and seeing what happens when they mix it, nope, there's going to be no element of surprise. It's going to be a calculated response. All right, so we use Hess's law of heat summation. So if you add two or more thermochemical equations to get a final reaction, you can also do that by adding their heats of reaction to get the final heat of the full reaction. So please star, highlight, asterisk these in your notes. The enthalpy of the reaction will be equal to the sum of the delta H of formation of the products and the delta H of formation of the reactants. Okay, so the delta H of formation is a constant, and it is a known value that would be in some sort of appendix or table for each and every substance. So important here that you know two things. Number one, this Greek letter is the Greek letter sigma, okay, and sigma means sum. So we are going to add those together. Okay, so we're going to add up the products and then we're going to subtract the reactants. And I want you to think really hard where you have seen something minus something for a delta before. That's right, the delta H is really the enthalpy of formations of the final minus the delta H of formations of the initial. Reactants are what you are initially, and products are what you are final. So we always get the right signage when we are done. We'll know if it is exo or endothermic because it'll either come out with a positive value or a negative value in order to determine that. All right, so a typical Hess's law problem would look something like this. What is the heat of formation for the reaction of gaseous carbon monoxide reacting with oxygen to form carbon dioxide? All right, so first things first, you always have to write an equation. So I have CO plus O2, carbon monoxide plus oxygen makes CO2. And then I have to go through and I have to balance it. All right, so I'm going to need two COs on the left and two CO2s on the right. And the whole thing is to figure out what the delta H of the overall reaction is going to be. So what I need to do is look up a couple of things first. All right, the delta H of formation for carbon monoxide is going to be negative 110.5 kilojoules, and that would be in our appendix. All right, that would have our big old list. For oxygen, since this is an element, the delta H of formation is 0. Okay, it exists. Nature already made it. I don't got to make any more. All right, and then for CO2, the delta H of formation is going to be negative 393.5 kilojoules. Okay, and let's not sell the unit short because it's kilojoules per mole. So if we have 2 moles here and 2 moles there, we have to account for that. All right, so the overall delta H is going to be the summation of the delta H of formation of the products minus the summation of the delta H of formation of the reactants. And this is where you are going to do some very simple algebra to plug it all in. All right, so these are your products. So that is going to be, I have 2 moles, okay, times negative 393.5 kilojoules per mole. All right, that's going to be our products. And then we are going to subtract, so it flips the sign of our reactants. I have 2 moles of CO, so that is negative 110.5 kilojoules per mole. And I have 1 mole of O2, and that is 0 kilojoules per mole. So that just equals a big old 0. But it's important to have in the proof of what's going on. So when I use my calculator, I find that this is equal to negative 767 kilojoules, because moles and moles cancel out. And then I'm going to subtract um, negative 221 kilojoules plus 0, and my overall delta H will be negative 566 kilojoules. All right, so what does this mean right here? This means this negative sign that it is exothermic, and we are going to see that this reaction would release heat to its surroundings. So you want to make sure that whatever is going to hold this carbon monoxide and carbon dioxide isn't going to melt under this much energy, and you have to obviously multiply out for your moles. Okay, so here we have our balanced equation. 2CO plus O2 makes 2CO2. You look up the heats of formation for each of your substances. Notice again that oxygen is a free element because it doesn't have any energy to make it. And then we use the delta H of the products minus the summation of the delta H of the reactions to figure out the overall delta H of the reaction. And we get our negative, or 2 times negative 393.5 and 2 times negative 110, and I couldn't fit the 0 in there, but it equals negative 787 minus negative 221 equals negative 566 kilojoules. So this indeed is exothermic. Okay, you can also use these types of equations to figure out how much energy is released through the combustion process. There's also an appendix that is going to be in your book for the heats of combustion, so delta H, COMB. And you'll see here for propane, the delta H is going to be negative 221.19 kilojoules. And here for octane, we are going to see it's negative 5,450. So the larger your carbon to hydrogen bonds, your hydrocarbons, are going to be, the more energy is released, which should make sense, which is why we use octane to power a car and why we use propane to cook food. And when we're indoors, we use methane, okay, in our Bunsen burners because it has the lowest delta H of combustion, because we don't want to make too much heat inside. You shouldn't use propane inside or octane or any other kind of jet fuel inside. So that is our Hess's Law and our heats of combustion.